One of the most popular problems for interviewers is finding the lowest common ancestor. I've personally seen this many times in interviews at many different companies. It's definitely one you should know, and there is more than one way to solve this problem. Let's take a look. This is AlgoDaily. We're given a binary search tree and two of its nodes as parameters. And we're asked to write a method called lowestCommonAncestor that takes three parameters, the root and the two nodes, and we're asked to identify what the lowest common ancestor is between those two nodes. And the lowest common ancestor is defined as the deepest node that has both of the two nodes as descendants. If we look at this example, the lowest common ancestor between 5 and 8 is 7. It's kind of a weird concept because we don't really ever think or need to use the idea of a lowest common ancestor. But once you realize it's just the highest shared parent between two nodes, it makes a lot more sense. And you start to think about ways to solve this problem. The obvious tool that comes to mind is some form of traversal, since we're given the root node and we need to kind of either make our way to the two nodes that are passed. So let's say it was 5 and 8. We would need to figure out a way to identify 7 as the parent through traversal, or figure out some other way. So one way to go about this is to visualize the traversal path that would be required. If we're given 7, which is the root, we could follow, quote unquote, follow 5 and 8 upwards to visually see that 7 is the lowest common ancestor. In this case, it's really easy because if we move up from 8, we get to 7. And if we move up from 5, we also get to 7 without touching 4. So in this example here, if we were to try to find the lowest common ancestor of 1 and 9, we would find the path from 9 up. And so from 9 up to the root, it's just 9 and 6. And then we would do the same thing for 1, and we would trace upwards. So starting at 1, we go to 2, then 4, then 6. Eventually, we get to something that's shared in common with 9, or at least the path of 9. So if we start thinking about possible solutions, we might realize that what we can do is find the node to root path and use that to our advantage. So that is indeed the first way that we can approach this problem, is via finding a common path that the two have in common, starting from the root, and then looking for the last place, the last node that they have in common before diverging. So if we wanted to find, in this pseudocode tree, if we wanted to find the lowest common ancestor of 1 and 8, you can see here we set up the binary tree, and I'm going to walk you through the code and understand what's going on under the hood. So we take in the root, we take in the two nodes, and we'll instantiate two arrays to keep track of the paths. Then we'll call the getPath method on the two nodes, passing in the root, the path so far, and the node that we want to attain. So let's look at the getPath method. If there's no root, we stop. Otherwise, we traverse and keep pushing the nodes that we see onto the path array. Once we see the node that we want, then we return true. Otherwise, we continue onto the path. Going back to the parent function, once we've attained the two paths, then we do a comparison. We compare the two until they differentiate, because that'll tell us when we've gotten to the lowest common ancestor, because after that, the paths will diverge. So we use a pointer called I, and while I is less than the path lengths of the first path and the second path, so while there's still room for traversing and comparing, we check if they're the same. If they are, we continue. If they're not the same, we know we need to stop because we've hit the lowest common ancestor, and we return that value. So going back to this example tree, we would do 7, 4, 1 in one array and 7, 8 in another array. And comparing those two arrays, it would be obvious that the only one that's in common in those two arrays is 7, and that's our lowest common ancestor. Another way to solve this problem is via using the properties of a binary search tree. Suppose we wanted to find the lowest common ancestor of 4 and 8. It's clearly 7 in this case. But notice that 7 is between 4 and 8 because it follows the normal properties of a binary search tree. And we can express this idea. If a node is between two nodes in the sense of value, so 4 is between 7, so 7 is between 4 and 8 in size, we know it must be a common ancestor of 4 and 8. So it spawns an idea for how to traverse this tree properly. If we're starting at 7, and let's say instead of looking for the lowest common ancestor of 4 and 8, say we were looking for the lowest common ancestor of 1 and 5 instead. When we start at 7, since we know that we're looking for a number between 1 and 5, we know we can't go rightwards because 5 is less than 7, so it must be on the left of 7. From here, the intuition is pretty much there. Using the properties of a binary search tree, we can tell if we should go left or right, and we'll simply stop when we've found something that fits the condition of being in between the two nodes that we're looking for. So starting at 7, if we're looking for the LCA of 1 and 8, we look at 7 and we compare it to 1, and we see that it's larger than 1, and we compare it to 8, and we see that it's less than 8. And so we know that 7 is the lowest common ancestor of this binary search tree. It can't be a smaller number because then we would have to go leftwards and enter this path. And that doesn't apply because 8 is no longer a child of that node on the left. Vice versa, if it was a greater number, then we would have to find it on the right, but then 1 would no longer be a child of that node on the right. Thus, we know that it's a good fit. And if we apply that logic to 1 and 5, starting at 7, we know that the greatest it could be is 5, so we have to go leftwards. And then we see that 4 is between 1 and 5, so this must be the lowest common ancestor. Here you see the steps outlined. 7 does not fall between 1 and 5, so we go left. 5 is less than 7, so search in left tree. We search in the left tree. So here is the solution in code. As you can see, it's not too complicated. We simply start from the root and then look to see if the root value is greater than the first node and greater than the second node, then we traverse leftwards. However, if the root value is smaller than both nodes, then we go rightwards, since it must be on the right. Otherwise, we know that it falls in between, so we return the root val.